Hello and welcome back to the course Computer Communications. We continue considering the functionality of the network layer, and in this recording we will talk about the details of the Internet Protocol, IP. Here is the structure of the IP header. As I have already mentioned, the size of the IP header is 20 bytes. It contains all necessary fields to implement the network layer functionality. So we have two fields describing the source and the destination addresses. So they are 4 bytes long in the IP version 4, which is currently running in the internet. So we have identifier field that identifies a packet. We have a length of the datagram, including the length of the IP header. We have flags. We already were introduced with the flags when considering the fragmentation of the IP datagrams. And this field actually contains the offset of the particular packet. The offset field, it's worth mentioning that the offset field is 13 bits long, and this is actually one of the reasons for counting the offsets in octets in number of 8 bytes. In this way, we may address larger datagrams, meaning that we may split large datagrams in a larger number of fragments. The discussion in this recording will be all around IP addresses. IP address is a 32-bit identifier for a host or router's interface, where interface is the connection, is the physical connection between the network device and the physical link. You need to assign as many IP addresses as many interfaces a network device has. IP address is a structured entity. In any IP address, one may differentiate a subnet part and a host part. A subnet is a network where computers, when communicating with each other, may reach each other without help from a router. So they are physically located in one network. And obviously the host part, the lowest bit of the address, they identify the machine within a specific network. Originally, when the internet has just been designed, so IP addresses had a very rigid structure. So you could determine about the length of a subnet part by looking at the first bits of the IP address. Currently, in today's internet, we don't have this rigid structure anymore. Instead, a subnet portion of the address can be of an arbitrary length. In order to indicate what part of the address belongs to the subnetwork part, one uses a slash notation, where the number after the slash indicates the number of bits in the subnet portion of the address. When structured in this way, so that the subnet portion can be of arbitrary long, so these classes, these IP addresses enable a so-called CIDR routing, classless interdomain routing. An important concept to remember here is that this part, the subnet part of an IP address, is used by routers to forward packets inside the network, while the host part is relevant to the last hop router, to the access router, in order to find the particular machine. Let us talk now about how a particular host can be assigned with this host part number. One way of assigning an IP address to a host device to the end system is by manual assignment done by a network administrator. The network administrator may take one of the available IP addresses and um, manually configure your computer to use this IP address. But in most of the cases, in most of the networks, computers get an IP address automatically by using a dynamic host configuration protocol, DHCP. Operations of the DHCP protocol are rather straightforward. So when a new client arrives to the network and connects its interface to the network outlet or connects to the network wirelessly, it creates a so-called DHCP discover message, which structure is illustrated here. So here you see that the source IP address is initially set to 0 because we do not have a valid IP address in this network. So the destination address is also a very specific number. So you see here it's all 255.255.255, and this address means that all IP enabled devices will receive this message. So this is an IP broadcast address. And it specifies the transaction ID. So the host packages this DHCP message inside the UDP datagram, which will be sent on port 67. It further packages adds the network header and the link layer header and sends this message to the network. So on the link layer, the message will also be addressed to broadcast. We will use the broadcast as the destination address. When the server receives the DHCP discover message, it prepares an offer, a so-called DHCP offer message, where, as you see here, it offers a valid IP address, and it sends this message back to the client. So to complete the protocol, the client should confirm the usage of the suggested IP address and get its confirmation, get acknowledgement from the server. Let's now talk how the server itself may get a range of valid IP addresses. Remember the hierarchical structure of the internet, where at the very low level of the hierarchy we have organizations where we connect ourselves to the internet as users. So in their turn, the organizations are connected to the second level internet service provider. So the internet service providers, they are allocated a specific address space by an organization which is called ICANN, which stands for Internet Corporation for Assigned Names and Numbers. So when ISP, the Internet Service Provider, gets its portion of bits corresponding to its network, a subnetwork address, it may further split this available address space, so this zeros over here, and create more networks, exactly as it is exemplified here. Despite the flexibility that classless addresses give us for assigning the IP addresses to subnetworks and further subnetting the subnetworks, the size of the IP addresses in IP version 4 places a rather a strict limit on the number of subnetworks and hosts that we may address. As a matter of fact, by now we already run out of available IP addresses. It means that one cannot any longer buy an available chunk of IP addresses for an organization. So this situation was understood for quite some time ago, around 10 years ago at least. And partially as a solution to the at that time envisioned problem of running out of IP addresses, uh, there was an architecture suggested to deal with the problem, and the name for the architecture is a network address translation. So, using this approach, we would share a single public IP address among several hosts or end systems behind a network address translation box. So using this approach, all the datagrams leaving the local network will have the same single source IP address. So let us see now how a network address translation box works. So assume that host with this IP address 10.0.0.1, and this is a IP address from a so-called private address space. It sends a datagram to a host with this IP address 128.119.40.186. The network address translation router would change the source address in the outgoing datagram to the one of public IP address, and also it will insert a record inside its address translation table, which tells that a datagram with this source address 10.0.0.1 and this original source number was changed to this address and this new port number. So port numbers in our case will be this key by which the network address translation router will search and find the corresponding row on the way back, as I will show you shortly. So when a reply arrives from our destination host, so 128.119.40.186, so it starts to search the entry which was recorded for this for the destination port 5001, and apparently, so it's find this entry here, and it should change the destination address from the public address and this port number to the actual address of machine that originally sent the datagram and the original port number. That is exactly what happens here. It is important to remember that network address translation is somewhat controversial architecture. It introduces more functionality inside the routers. So according to the internet principles, all the complexity, all the processing of transport layer header should be done only at the end hosts. Here we suddenly have routers processing the transport layer headers. So network address translation helped to deal with the shortage of IP addresses. However, a more systematic way of dealing with the situation was later on proposed by the standardization organization, IETF, a new version of the IP protocol with the size of the address space being equal to 128 bits